We are starting a new chapter and a new unit today, and it's kinetics, and that is all about the rates of chemical reactions. The rate of reaction for a chemist is defined as the change in concentration, typically molarity, over the change in time. And so if you were to plot, there we go, the change in concentration of any substance, it could be a reactant or a product. Well, in this particular example is a reactant because its concentration is going down over time, right? It would look something like this. And you could get the rate, the change in concentration over change in time, by measuring the slope of this at any point in time. The square brackets mean concentration of. So that's saying concentration of products. This is concentration of reactants. And as I said on the last slide, the rate can be expressed as the change in concentration of either any of the products or any of the reactants. So obviously reactants over time are going to be decreasing in concentration, and so you'll see a negative sign, or there'll be a negative slope if you graph the change in concentration of reactants. Change in concentration of products, the products will be increasing over time, and you'll see an upward curving slope. So the units of rate, and this is worth really making a note of, because later on in this chapter, you'll learn that units are very important for this chapter. And so it's important to kind of notice the units of everything along the way. It'll make it easier for you. But since rate is change in concentration, okay, and concentration is typically molarity, over time, time is usually seconds. Now, time could be minutes or years, but quite often seconds. So rate of a reaction has units typically of molarity per second. So just kind of telling you generically, this will be the first challenge for you in this chapter, and that is expressing the rate of reaction in terms of any of the reactants or any of the products, and then comparing the relative rates of the appearance and or disappearance of any of them to each other. So let me give you the generic formula for the rate of reactants and products, and then we'll do some specific examples. So we have this kind of generic equation there. And for any reactant, you're going to put a negative sign in first. And then, of course, the product, C and D, will have positive signs. They'll be increasing over time. So you only need to do this if you are comparing the rate of a reactant or product with another reactant or product. To make them equivalent to each other, you have to pay attention to the coefficients in the balanced reaction, right? Because the larger the coefficient, the faster the concentration of this substance is going to change, right? And so if you're setting them all equal to each other, and let's just say A is large, okay? So if A is large, then large A, the reactant A, is going to disappear quickly, more quickly than the rest of them. So if you're setting the rates equal to each other, you've got to use an equalizing term of 1 over the coefficient of A. So take a look at how this is set up, and we're going to do some practice. This seems easy, but students get tripped up on this pretty easily. So take a minute and make sure that it makes sense to you. A lot of students will say, well, wait a minute. Why is it 1? Oh, good, my eraser's working. Why is it 1 over the coefficient? Why isn't it just the coefficient? Because you're trying to make them all equal, right? So if a coefficient in front of a substance is making it disappear quickly, then in order to set its very quickly changing rate to the other slower ones, you've got to correct for that coefficient. You're essentially canceling it out by 1 over A. A couple of examples. Here's a real reaction. And let's say the problem asked you to express the rate of reaction in terms of all of the reactants and products. So you would do something like this. There's a coefficient of 1 right in front of the two reactants, right? So rate with respect to nitrogen, with respect to oxygen. Notice they both have negative signs. They're both reactants. And the rate with respect to the one product, nitrogen monoxide. Okay, there's a positive there. And we have taken the coefficient of 2. It's 1 over whatever the coefficient is. And remember why we did that. So this might be an easy way to kind of understand intuitively the math. So nitrogen monoxide is appearing 2 times faster than either one of the reactants are disappearing, right? Because of this coefficient. For every 1 of each of the reactants, we get 2 of the product. So its rate of appearance is 2 times faster. So if we're setting all the rates with respect to the reactants and products equal to one another, we've got to cancel out that 2 times faster rate. And we do that by 1 over the 2, 1/2. If you were to look at a graph monitoring the concentrations of reactants and products over time, and this type of graph you should be able to interpret. So you would expect that any product, its concentration is going to increase over time. Of course it does. And any reactant's concentration should decrease over time. Now, if you want to find the rate of a reaction, be able to compare the rate of disappearance of a reactant compared to any other reactant or compared to the rate of appearance of a product, you can look at the slope of these two lines at any one point. Because remember, rate is change in concentration over change in time. So let's pick 2 points on each of the graphs. And so notice that the rate of change of all of those is different for different times. So you got to pick the same time slice if you're comparing one to another from a graph. So we'll pick the time frame they have marked right here, and that's between 5 and 10 microseconds for each of them. So looking at nitrogen monoxide first, I'll pick the 2 dots, one at 5, one at 10. Okay, so the change in X for both of them is going to be 5 microseconds, right? So I'll just put that down. All right, so now we've got to find the change in Y for the reactants and products and compare them, because we're going to pretend like we don't have this balanced reaction, right? So I'm going to go ahead and carry over nitrogen monoxide points to the y-axis. And that looks to me like right below 15. So I'll say 14 minus 8 or 6. All right, so the rate with respect to nitrogen monoxide is 6 over 5 molarity per microsecond. And the rate with respect to the reactants, nitrogen and oxygen gas. So let's pick lines on that curve for the same time frame. Whoops, didn't mean to do that. All right. So let's see, that would be right here and right there. All right, so the change in Y at that point, here and here, looks like it would be, let's see, it's 15, maybe 13 minus, that's probably 10. Okay, so 3/5 molarity per microsecond. All right, so according to this graph, now obviously if you have to interpret a graph, it's going to be a lot more increments than this. This was a lot of guessing. So you can tell just by taking the slope at the same point of time that the rate with respect to nitrogen monoxide is, in fact, 2 times higher than the rate with respect to nitrogen and oxygen. So just be able to interpret these graphs also, and again, pay attention to the units, please. Now, as I mentioned earlier, because these are not linear relationships, the actual rate of reaction is going to decrease over time. So let's look at with respect to a reactant, okay? So you can imagine if you measured the slope at the beginning of a reaction, it's going to be much higher, a much faster rate than the rate of reaction at a lower point. Okay, so the rate's going to slow down as the reaction progresses. And on a molecular level, that makes sense, right? Because let's say we start with 10 reactants. Okay, and they react with each other. They bump in order to react, things have to collide, so they react with each other to form 5 products, right? So 10 reactants react. So what's going to happen when some of these are gone, okay? Then there are going to be fewer collisions, fewer opportunities to react, simply because you have fewer reactants. And so, and we'll talk about collision rate later on, what affects the rate of a reaction. But for right now, just as the amount of reactant decreases, the rate's going to go down. And so the chemist has to ask themselves, where do we measure the rate? I mean, do we measure the average over the entire reaction? Do we measure it at the beginning? When do we measure it? Well, you'll see that most chemists will try to get what they call the initial rate of reaction right in the beginning. And so it's much easier to deal with initial rates because you do not have significant amount of product buildup at that time. And you'll see, especially when we get into equilibrium, that when you don't have any product, it's very easy to monitor the clean disappearance of A. As soon as you start building up product, if the reaction is reversible, then it gets quite complex because you have some going in the direction towards B and some going in the direction back towards A. So initial rates are a very popular way to do it. However, you can measure the rate at any point on this graph of concentration versus time simply by drawing a tangent at any point in time that you're interested in. So hopefully you know what a tangent is, right? You just take, let's say we were interested in the rate of reaction at 10 seconds specifically. So you would make a point on your graph, on your curve at 10 seconds, and then draw a tangent line. That's a line that's just touching that curve at one point. And then measure the slope of your tangent line. And that would be the rate of reaction at that particular point in time. So just so you can visualize the type of decrease in rate we might observe over time. So here's a reaction that early on in the reaction, the rate is 0.08 molarity per second. And then later on, just a few seconds actually, look at how much we don't get much change in Y for the same change in X, right? And so the rate has dropped. It's less than half of what it was originally. And then as you can imagine from this type of downward sloping curve, the rate of reaction is going to plateau at some point. When it reaches equilibrium, there's going to be no change in concentration at all. An example, if you're asked to find the instantaneous rate, just so that you can see it being worked out, let's say you were asked to find the instantaneous rate with respect to both one of the reactants, in this case hydrogen gas, and one of the products. Okay, so you can see from the balanced reaction that you expect the rate with respect to hydrogen iodide to be 2 times faster, right? That's going to be appearing 2 times faster than the hydrogen will disappear. So let's make sure we get that off. They told us to find the instantaneous rate at 50 seconds. So the first thing you want to do is make a little dot on each of the curves of 50 seconds and then draw your best tangent line, okay, through, and I can't draw a straight line anymore. So, and then once you draw the tangent line, just get the rise over run, right, the slope of them. And so by doing that, we get the rate of disappearance of hydrogen gas at 50 seconds, right, 0.007 molarity per second, and the rate of appearance of hydrogen iodide at 50 seconds. Let me move this whole thing up. There we go. I just noticed I left a step off here, so let's do this. So as you can see, the rate with respect to hydrogen iodide at 50 seconds, I'm going to ignore that to begin with, is 0.56 divided by 40. And so that is 0.0140 molarity per second. So the rate with respect to appearance of hydrogen iodide is in fact twice as high. And that is, I wanted to show the difference, that they're a factor of 2 off, and this was not the right way to do it. So hopefully I didn't confuse you there. Here's a sample problem. So this is what you should be expected to do after listening to this lecture. Number one, you should be given any balanced reaction and be able to write expressions for the rate of reaction with respect to any reactant or product. Number two, you should be able to interpret graphs of concentration versus time and find the instantaneous rate of reaction at any point on those graphs. And now this is kind of building off one. In addition to being able to write the expressions for rate with respect to any reactant or product, sometimes you'll be asked to quantify them. So let me give you an example of that. Here's the reaction we're looking at and the information they gave you. They said the experimentally determined rate of disappearance of permanganate ion, that's right here, it's a reactant, is right here. Now notice, well, I won't go into that right now. Okay, calculate the rate of disappearance of hydrogen peroxide, H2O2. So let's go ahead and set that up. Now, you could write a rate expression for every single reactant and product. Remember what it was? You do 1 over the coefficient times change in concentration of that substance over time. And if you're comparing it to other reactants and products, you just keep going. So I'm on MnO4 permanganate now. Change in concentration of permanganate over time. And you could just keep on going, right? All right. But you don't need to do that because they've only asked you to compare 2 substances. So we only need to write it for the 2 substances that are involved in the problem, which is permanganate, which they gave us the value for, and then they are asking us about hydrogen peroxide. So I'm going to follow the rules just for those. Minus 1/2 change in concentration of permanganate over time equals minus 1/5 change in concentration of hydrogen peroxide. Now it's simply algebra, okay? So what are we trying to solve for? We are trying to solve for the rate of disappearance of hydrogen peroxide. And I did this, there's an easier way to do this. So, all right, so again, it's just algebra. The first thing I want you to understand is that the rate of disappearance of any particular substance is simply this. So if we're not setting the rate with respect to one component equal to the rate of, or we're not comparing it to any other substance, and we're just saying what is the rate, remember what rate is, change in concentration over change in time. So if it's just rate, you're not comparing it to anything, don't use the coefficients, okay? So this is what we're trying to solve for. Change of concentration of hydrogen peroxide over time. So we want to get that part of the equation right here. Let me change colors. By itself, just as you were solving for x. Pretend like this is x. So how do we get that by itself? We multiply both sides of the equation times minus 5, or 5 if you want, whatever, right? So that cancels that out. So times minus 5. So what do we end up with? We end up with, this is backwards way. Okay, when you multiply both sides by minus 5, you end up with the rate of disappearance of hydrogen peroxide is 5/2. See, because we have 5/2. The negatives cancel out, times the given rate for permanganate, which is 2.2 times 10 to the minus 3. All right, so now that's kind of the stepwise thing, but now I want you to look at this, because intuitively, sometimes some of you can just look at the balance equation. You don't have to go through this algebra torture. So let me kind of walk you through that in case it works for you. If it doesn't, you go step by step, okay? All right, so looking at the balanced reaction, we're comparing these two. The first question you should always ask yourself is, which one of these is going to change its concentration more quickly? Okay, hydrogen peroxide, right? For every 2 permanganate that disappear, 5 hydrogen peroxide are going to disappear. So the rate with respect to hydrogen peroxide is going to be larger, okay, than the rate with respect to MnO4. Right? So it's always going to be a ratio of the two coefficients. And your job is to decide, is it going to be 2/5 of what the given amount is, or is it going to be 5/2 of the given amount? You're solving for hydrogen peroxide. It has the largest coefficient, so it's going to be faster. So you basically take that ratio and you multiply it by the given amount. So whatever method, and you may just need to go off by yourself and think through this. It's not real hard, but students tend to get confused. So whatever method works for you, make sure that you can do this. There is a practice worksheet posted. To summarize this intro to kinetics, and there's quite a few conceptual questions that can come out of this intro PowerPoint, so don't blow it off, okay? So there are several key factors that can affect the rate of a reaction. One of the most important is reactant concentration, obviously, right? The more concentrated the reactants are, the more collisions you're going to have between them, and the more collisions you have, the more reaction will proceed and the more product you make. Oh, yeah, I put this to remind you. We've talked about gases quite a bit, right? So if you're talking about gases, we don't typically talk about concentration of gas solutions, right? We essentially measure the concentration of a solution of gas by measuring pressure. Because remember what pressure is. It's collision of the gas molecules on the container. So the more gas molecules you have, the higher the pressure. So if it's a problem, if it's a reaction involving gases, just remember that when you read pressure, you're thinking concentration, more gas molecules. Another factor that's important in the rate of a reaction is the temperature. And as you would expect, increasing temperature increases reaction rate. As a matter of fact, and this is pretty reliable, there's a rule of thumb that for each 10-degree rise in temperature, the speed of the rate of the reaction about doubles. And that's a good rule of thumb. That's kind of a good piece of information to tuck in your pocket. Remember, anything that increases collisions, the rate of collisions, will increase the rate of reaction. So temperature, of course, is increasing collisions, right? Because if you increase temperature, you increase kinetic energy. And of course, more movement means more collisions. And we're going to we have a formula for that at the end of the chapter. Another thing that speeds up reaction rate is catalyst. And a catalyst works simply by changing the pathway of a reaction to make it easier. So let's say you have Kennesaw Mountain. You can either climb up the mountain, right? And it's going to take you a certain amount of time. But what if somebody drilled a hole in a road through there? If there was a tunnel and you could go through it, you'd get through a lot quicker, right? So this tunnel would be like a catalyst. So that's what catalysts do. They provide a new pathway that's easier, quicker. And that is it for the introduction to reaction rates.